So, so the title of my talk is, at least formally, Science, Statistics, and the Problem of Pretty Good Inference. And at the last minute, I really wanted to change the name of the talk after seeing this pop up on Twitter, and I was told that I could so long as I include the typo. So the other way of thinking about the talk is nothing works and everything sucks. But I hope it will end up seeming a little more hopeful than that. So one thing I should say is that this is not my usual style of talk. The usual way I go about talks reflects what I typically do for a living. I'm a computational cognitive scientist. So I run a whole bunch of experiments, testing things, I build models, and generally my goal in any talk is to cram as many experiments and models in as I possibly can before everybody starts realizing I've got no idea what I'm talking about. I'm not going to talk about either of those things today. There will be some bits of modelling that pop up in it, but this is very much a set of case studies based on my own experiences. So the previous talks have been kind of very big picture sort of things, talking about either the history of reproducibility in psychology or in thinking about the large-scale behaviour of scientific systems. I'm very much taking the approach of looking at it, a tiny little microcosm as one of the scientists in this system and trying to figure out what I'm doing and whether or not it makes any sense. So yeah, I'm not a philosopher, I'm not a statistician, I don't know what this new fancy term meta-science means, so I'm not sure whether or not this fits, but we'll see how this goes. So at one point in my career, I did spend a bit of time trying to read up on the history of statistics, and this is from Stephen Stigler's book, in 1986, the history of statistics, measurement of uncertainty before 1900s. And this is just sort of from the very beginning. And the way that he talks about this is to point out that statisticians have this understandable tendency to view the whole of the history of science as revolving around measurement and about statistical reasoning. And with the implication here that this is slightly self-serving to some extent. And for the most part, I'm interested in these topics, but then there are times as a working scientist that, my attitude is, I'm out of here, I don't care anymore. I'm getting cheese fries. One thing I find, though, reading a lot of the history is, and thinking about the different kinds of perspectives on statistics and the role it plays in science, is I feel like I notice a couple of different camps, and it's not the usual Bayesian frequentist divide. One perspective that pops up a lot, and I tend to think in these terms, is an instrumental view of the role of statistics. And the idea here is that we're thinking of statistics as fundamentally a tool, not any different to any other tool that we use as part of our research. It's there to help us with the development, evaluation, and modification of the different theoretical claims. So it forms one part of a dynamical system. And so the image at the bottom there is taken from George Box's 1976 paper on science and statistics, and sort of points out that there is this feedback loop, this process quite similar to the sorts of stochastic systems that Berner was talking about, in which scientists propose, modify, test, adapt on the fly. And this doesn't necessarily assume that statistics is particularly special. This is just part of the process. An alternative perspective that you see occasionally in some of the papers and books is that statistics plays a more normative role in science. And this sort of view says that statistics tells us something about how we should do science. It provides the logic of and the rules for scientific reasoning, right? And there are a lot of people who've made versions of this claim. Like, I think one of the stronger versions of this is Jane's in his book, Probability, the Logic of Science, that basically says that ultimately statistics are telling scientists how to do our jobs. Now, obviously these two are not actually distinct binary things with nothing in between. Everything in life is a rich tapestry, and the moment you set up a binary opposition like this, of course what you're really talking about is a simplification, but I find it a convenient one. So I have opinions on this topic, and they've changed a bit over time. I'm really not a fan of the idea of thinking about statistics as a normative claim, and I'll try and illustrate in this talk essentially why I think that. because it's not something I've always thought. I actually used to think the other way around. So this is the sort of thing that I think I have occasionally encountered, this attitude, I don't know who this guy is. But basically saying that, look, statistics is all about rational inference about data. It's about belief updating. This is the kind of thing that you see sometimes from a certain type of hardcore Bayesian that I guess I once was. And I have somewhat changed my opinions. So there's two parts to what I want to talk about, and I think that in comparison to some of the other speakers, this will probably be a short talk. But one of the reasons that I'm a little bit skeptical about taking my own statistics too seriously comes from thinking about the data sets that I have to work with. Data, as is always pointed out in anything in the philosophy of science, is not neutral. We don't, science, I'm just going to quote community, science does not deal in all possible laboratory manipulations. Instead, it selects those relevant to the juxtaposition of a paradigm and the immediate experience that that paradigm is partially determined. You are designing your experiments with a goal in mind, to test certain ideas. You are doing that within some kind of framework that has been given to you to begin with. And so as a result, scientists who approach a problem with different theoretical perspectives, different paradigms, are going to engage in different concrete laboratory manipulations, and that is going to change what the landscape looks like. You don't have random collections from the world, you have a collection of data sets that have been put together by the operation of individual scientists pursuing particular goals who've been informed by a zeitgeist or some notion that's floating around in the background of their lives. And I guess this is my dig at operationalism to some extent. Anytime we do a laboratory study, like when I do this in cognitive science, I mean, I study human induction, reasoning, decision making, and learning, and I try to do it as much as I can within the context of a controlled experiment. And I do have to do some kind of operationalization process. At a bare minimum, I have to define some set of measurements that I'm going to use, and I'm doing it in the context of a situation where we aren't all agreed on what the underlying phenomenon is. I'm making decisions on the fly, and when I do that, I am distorting a cow into a sphere. And that doesn't necessarily mean my experiments are useless, but they do mean that they necessarily reflect a particular theoretical view or a particular goal in mind, and that may not be the same thing as what you have in mind when you're doing your experiments or reading my papers. So to give kind of a concrete example of this, this is a study that I was thinking about. So we were, my colleagues and I were thinking about the problem of making novel discoveries, of imputing or inferring the existence of entirely unobserved categories. So picking sort of random example like theoretical predictions that Neptune existed before it was in fact discovered. And I was doing this in the context of thinking about human categorization, concept learning, reasoning, kind of harking back to one of the earlier talks. There's not even a clear definition or a clear demarcation of what the difference between reasoning, categorization, learning actually is. So I'm already on a bit of shaky ground trying to work out what I'm trying to study here. But I'm going to try and push it into a task at least, so that I can get something out of this. And my task looks like that. It has nothing to do, it doesn't look an awful lot like staring into telescopes searching for Neptune. Instead, I design a task that looks like this. And so this is from a situation, like what I was trying to model in the situation is where participants, people, have different kinds of data to work with. So I might have one observation which I've actually seen it with my own eyes, I know its physical properties, so that's the one which is labeled a sec. I have discovered the existence of some other thing called a yar, and now I've seen this new thing. So part of what we were trying to get at in this study is looking at what kind of factors influence when people are willing to say, okay, this is a sec, this is a yar, or more importantly, this is none of the above. this maybe doesn't belong to any of those categories? When do people decide to go outside the boundaries of what they have previously been given and impute novel categories? So we ran a whole bunch of studies based on this because we sort of looked at the philosophical literature and some of the psychological and statistical literature on these as mathematical problems. Like, they're well-studied problems. In statistics, it goes under the name of species sampling, but it's a reasonably well-known problem in different disciplines. So we have, eventually, at the end of a couple of years of being yelled at by reviewers and changing our minds about things and running different experiments. This is a set of 7 models that we predicted, or we thought about ahead of time, that we wanted to test. And a set of 4 experiments where we'd thought up the first 2 ahead of time and then sort of sequentially modified as we went along, as we were nudged in different directions by different people. And there's also like a hidden set of 20 other models which reviewers just forced us to add, which were completely irrelevant. They didn't work. But you know, we tested them after the fact. Reviewers typically force you to hark a lot. So I ran a bunch of good experiments along this lines. I think they're good experiments anyway. And I get quite clean data out of this. I could run these with very large sample sizes. I could replicate experiments if I wanted because I was doing all this stuff on Mechanical Turk. I knew exactly what I was looking for because I had these formal models in mind. And you can see, look, if I plot the, this is obviously a summary picture, not the low-level details. But, I'm getting correlations of 0.99 between model and human data. That's not bad. Admittedly, there's a ton of hidden complexity going on there, but overall what I find is that some subset of models, and it's the 3 at the bottom, all tended to account for all of the experiments we ran. None of the other ones did. The models that survived, like at least came out being not terrible, all had a property in common, but they all used hierarchical reasoning, which I won't bore you with in this context, but there was some underlying invariance that each of these models that did okay all shared. And so I was pretty proud of myself, right? I feel like I had learned something useful about categorization, about reasoning, about the problem of going beyond what you're given. Cool. But I do have this problem, right? And it's the problem that's been set up by my operationalization. I pushed this thing into the lab, and now I'm not sure how this maps back out onto the world. And it's the classic problem of external validity. It's not like any of us are unaware of this. It's in all the methods textbooks. This is not unusual at all. And so I've done some fancy statistical analyses on the way. I've done some Bayes factor analyses. I've done a whole bunch of cross-validations. I ran lots of things. It really doesn't matter which ones I used. But what they're really telling me is something about the relationship between my models and my experiment, which are all contingent on this particular operationalization, this particular measurement probe, which was set up with a particular goal in mind. And so thinking about how to generalize from what I have said in this paper to the problem in the world that motivated it in the first place is much more tricky than the statistical analyses that I've reported in the paper actually imply. Generalization beyond the data you're given is actually a hard problem. And that's as true for statistics in the world as it was for participants in my experiment. Generalization is hard. Well, okay, so that's a problem. But sometimes I think I'll just step outside of this. Why don't I go at least out into the world? Like do something with real world concepts and categories and collect data about systems of thought and reasoning that already exist. So here's an example. This is the Small World of Words project that I was involved with, and this is one where what we wanted to do was learn something about the structure of human semantic networks. So what we did was we collected 4 million or something or other free association judgments. And we end up with this 12,000 by 12,000 matrix that measures the association strength between a whole bunch of words in the English language, and we've been trying to do this across a bunch of different languages as well. And we get really pretty pictures like this, which I really like. Yay! And hey, this thing, I don't know if anyone's ever going to try and replicate this, because this is a really hard study to replicate. On the other hand, it already has 4 million observations in it, so some part of the data is probably reliable already, but maybe not entirely. So you can use these norms to learn quite a lot about how humans think about the world, at least when using English. So it turns out these norms contain a lot of information about like common sense knowledge about science. So if I give the network keywords of statistics, physics, and psychology, and then just ask it to construct a local neighborhood network, like I'm skipping the technical details, from this, just filling in all the missing links, the things that are common between the two, it automatically infers the missing link, the thing that connects all these things together, is science and study. So there's a lot of structural knowledge that is encoded in simple free response tasks. I say cat, you say dog. When you get lots and lots of those data points, you get a surprising amount of structural knowledge. Yay! Small world of words. It's a great project, I really like it. I'm bragging about it because Simon Dedane actually did 99% of the work, so I feel no shame in plugging it. So you can do this with lots of things. It can provide me with opinions about clothes. Apparently it tells me that pants are a kind of canonical, prototypical type of clothing. Skirts are, but to a slightly lesser extent. Scarf is weird, it's not a proper form of clothing. It's technically clothing, but not really. And you can just tell from looking at the structure of the network. It knows things about how families tend to be organised, so without priming it with anything, you just give it words like mother, father, son, daughter, and it automatically reproduces the kind of structure that you would expect from kinship terms. So again, there's a lot of knowledge here in this network, and it seems like the kind of thing I can use as a tool to study a whole lot of other things. So this is the kind of study we would then do using the small world of words data. So what we decided to do is give people 3 words that were completely unrelated to each other. They're matched on a whole bunch of characteristics that psycholinguistics people actually care about, but I don't, so I just do what I'm told and nod and smile. But you ask people to say which of these 3 words is the odd one out. I'm always curious to know if this replicates, because, okay, you have to pick one. One of these words is the odd one out. 2 of them are the same. I want you to raise your hand when you tell me what the odd one out is. I have no idea if this is going to work. Okay, so you think that cup is the odd one out? Hail? Teacher? Okay, so we have, so nobody picked cup. There was a lot for hail, none for teacher. Yeah, that's in the small world of words network too. I don't know why this continues to replicate. The example keeps working. The hail doesn't fit. And of course, we didn't just do it with these 3, we did it with hundreds, thousands, things like that. There is something about the structure, the global structure of this semantic network that actually captures people's intuitive judgments about bizarre tasks like this. Okay, cool. I'm feeling like I'm doing real science here. The problem that I have is that my data also includes a whole lot of other things that maybe I don't want in my experiments. So the small world of words networks is actually pretty misogynistic. If you give it male and female as the keywords, it produces a whole lot of really, really nasty stereotypes. And okay, maybe I want to study sexism, and if so, well, this data is useful for that. But very often, the way that these kinds of norming studies are used in the real world is not for that. It's used as if it were a natural way to find meaning in things. And so when you see this sort of pattern of results being used elsewhere, you get nasty consequences. So just because I haven't tried using the small world of words example for this is something that just uses natural language text to do the same thing, and I'm stealing somebody else's ideas. But basically this is using natural language to operationally define a measure of sentiment. Is something good or bad? So this is a standard model in machine learning that is used to estimate these things. It's word to vec. If you know it, great. If you don't, it's irrelevant. And this is basically a short story of how to create a racist AI. And it's really not that hard to do. You fit the model to the data, where the data is words that exist in the world, lots of them, big data, very reproducible, and pick whatever statistic you like. I mean, in this case, they use cross-validation as the measure of, to a holdout sample as the measure of accuracy. And this model makes really good predictions of the valence that people will assign to different sentiments, etc. And look, it works. So fidgeting is a negative word, interruptions are negative, totalitarian is considered to be particularly bad, world famous, on the other hand, is kind of nice. It does capture that structure. And you can use it for sentences. This example is pretty cool. Yeah, that is pretty cool. This example sucks. No, that's not favorable. Woohoo! I guess I'll just leave that one there for a second and kind of go, Emily is nice. Everyone likes Emily, and Heather and Yvette and Shaniqua for some reason, not so much. The AI that's been trained on this thing is actually extremely racist, and that pattern of results shows up over and over again. And of course, if you want to use this as a measure of sentiment, rather than just dumb shit that people say, then you have a problem, because they should be the same sentiment. You have a structural relation here where you think that the person's name is irrelevant. And because of that, because the model does not encode that structural knowledge, it learns crazy stuff. And so this is a consistent problem I find when I do my lab studies. The data analysis I do is only useful if I know how my operationalization is going to affect how I will try to generalize outside of that context. But when I go out into the field, so to speak, or in a slightly more naturalistic context, the data analysis is only going to be useful if I know which parts of my nice real-world data are actually relevant to the thing I care about. And of course, I picked up things like sexism and racism as examples of that, because for almost everything I care about in the kind of research I do, that is not a relevant part of the data. Sadly, it's a thing in the world, but it's not a thing I want to be using in my studies. And so that's a problem. And this is the thing that pops up over and over again, is that the limitations to my design and to my data will ensure that the scientific problem that I actually care about is so much more difficult than the toy problem that my statistical tools were built to solve. Like, I could go and read Neyman's book and try and go, okay, Neyman, what did you tell me about how to control for sexism in large-scale semantic networks? Strangely, there's not a lot there. The theory of null hypothesis testing wasn't exactly built to think about all of those problems. Which segues to part 2 of the talk. If the data have these messy, ugly problems, the statistics that we have are very rarely the statistics that we need. So technically I learned stats in undergrad, but like most people with a psychology background, that was worse than useless. So when I actually learned statistics, it was in my PhD, and I think this is kind of the sort of diagram I used almost as a Rosetta Stone, as a way of trying to understand everything about the literature. So what I would have here plotted on the x-axis is some generalized notion of model complexity, and on the y-axis you've got model fit to the data that I've received. Right? So as I increase my model complexity, I'm going to increase my ability to fit noise. The goodness of fit measure, whatever it is going to go up, but the generalizability is going to go down. And this is the kind of standard trade-off that we're all sort of familiar with, right? It's a goodness of fit versus model complexity trade-off, Occam's razor, whatever you want to call it. This bias variance trade-off, you want to find this sweet spot in the middle that fits the data to just the right amount. But it's really hard to know what just the right amount actually is. And I used to think I had an answer, that I understood what's going on here, and I'm less sure than I did now. So I think, okay, well, what statistics am I going to use to solve these things? Do I use p-values? My opinions on this topic are fairly well known. I will say, though, like, I actually don't hate p-values, not as much as this implies, but if I'm going to mock statisticians, I don't want to mock them for their worst attempts at operationalizing science. I want to go for something closer to the best. I actually do think that Bayesian reasoning is a good way of thinking about learning from data. And I do, in principle, think that the Bayes factor is a handy tool for operationalizing this kind of thing. So, okay. This is sort of a sad story of how I fell out of love with Bayes factors. the way I think about Bayes factors now is not the way that I used to think about them. I used to think of them as it represents the inherent amount of evidence for model A over model B as conveyed to you by the data. I no longer think that that's actually particularly meaningful. I think of it now as a tool for confidently selecting the best model, where best means something weird and models are essentially fantasies. And this is where I kind of get really grumpy. So this is, and now I'm just picking on somebody I really like. I'm picking on E.J. Wagenmakers. Again, my usual tactic is to try and go after people I really admire and respect. I'm not going to waste my time trying to be mean to people who are dumb or whatever. E.J. is awesome. So now I'm just going to be mean to him. So this is from a recent paper, and it doesn't actually matter all that much what they're talking about in the paper, other than this is a setup that you see when statisticians talk about doing inference that implicitly assumes a kind of normative model. So here we go. As a first example, consider what is perhaps the world's oldest inference problem, one that has occupied philosophers for over 2 millennia. The problem of induction. You know, we've got the riddle of induction. In machine learning, you've got things like the no free lunch theorems. This is considered an unsolved problem in general. And then we go to address this question statistically. We can compare two models. The first is the general law that just simply assumes you will only ever observe positive instances. And the other is a beta binomial model, or beta Bernoulli model, with uniform primeness. And my first thought is, what? I study induction, right? I study human reasoning. And if somebody came to me and said, in the psychological context, this is how humans should reason in the lab studies, they would be laughed out of the literature. This is not how induction works, because induction is complicated. But leaving that aside, the big problem we have when trying to evaluate the behavior of, say, the Bayes factor as a tool in this context is this question of the truth. A true process, a true model, it doesn't really matter what it is, other than the fact that whatever the truth may be, it is never in your model space. I am not so arrogant as to assume that one of the models, one of the theories I am trying to evaluate is actually correct, or even close to correct. I'm doing psychology. I've got no idea how this works. Like, for the most part, my models are terrible, as are everybody else's. And this is the typical sort of diagram that you see in machine learning and statistics textbooks that sort of talk about the issues of bias variance trade-off, of finding ways of solving that nice little picture I showed at the beginning. But the fact that the truth is not in your model space has some very, very strange consequences. So this is me being a bit silly and being a little bit snarky at EJ in a reply to that paper of his, where I set something up that says, well, what happens if you have negligible error? So you've got a situation where there is a set of measure zero, in fancy pants stats terms, where you actually just get the wrong observation. And in a frequentist sense, you still have the general law holding. Asymptotically, the probabilities are 1, blah, 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 blah. And yet the Bayes factor will absolutely confidently always select against the general law. It's supposed to be the right answer. By any reasonable human standard, it is the right answer. If I have an infinite number of yeses and one person who said no and was lying, then the correct answer is that the general law holds. The problem is that none of these models are right. They're just not well specified for the problem at hand. And when you look at the behavior of the Bayes factor in real life, when all of your models are wrong, it doesn't converge to the truth. It can't, because the truth isn't there. It converges to the model that is least wrong in the sense of a very specific information measure. Kullback-Leibler divergence. I'm happy to argue with you if you think that Kullback-Leibler divergence is actually a good thing. I don't. But the point of, if you choose with probability 1, with complete certainty, something that's wrong, that's just transparently insane. That is not how we're supposed to be doing inference. And this is, again, this isn't novel. This is just the problem of model misspecification. And when all your models are wrong, your inferences do funny things. And so when we're in this kind of world, and we're trying to build real models, not toy models, everything starts going a little bit awry. So this is the formula for computing the Bayes factor. So the bit of the Bayes factor that matters. So on the left-hand side, you've got your prior predictive distribution of the data conditional on your model. What you have to do is integrate out your uncertainty about model parameters, and you need some prior over model parameters that you're going to use. So that term there, this is the researcher's belief or knowledge about plausible parts of the model space. And the prior predictive distribution is extremely sensitive to that choice. especially to the tails of that distribution. So the things that you think are implausible, the question of whether you think it's really implausible or really, really implausible turns out to have a big effect on how the Bayes factor behaves in practice. And I don't know how to choose the difference between really implausible and really, really implausible. I'm just a human researcher. I'm not, in fact, endowed with perfect knowledge of my own beliefs about the world. And this gets really, really bad once your models actually start to become more realistic. As you get more realistic models, as you try to get to the point of thinking about really complicated representations of cognitive processes, you're operating in a high-dimensional space. High-dimensional spaces, as the saying goes, are very lonely places. Everything is far away from everything else. Everything is low probability. Almost certainly, everything that matters that you observe is somewhere out in the tails, the exact part of the prior that you don't know how to write down. So the more plausible your model is of human reasoning, the less plausible it is that you can write down a plausible prior for it. We're in a bit of trouble here. And yes, if we are this flawed human being, this is what an actual model of inductive reasoning looks like. This is taken from a paper by Brendan Lake, right? And again, I won't go into details, but what we've got here is an attempt to model how humans think about like handwriting or written alphabetic characters. And the tasks that we're trying to model are things like generate new letters, new copies of the same letter in a foreign alphabet, or generate new letters that would plausibly be members of this alien alphabet, just on the basis of one exemplar. So you get shown a couple of things, maybe one thing, and then you've got to guess a whole alphabet from it. This is the kind of induction that people study in the state of the art in this literature, and that's the kind of stuff that I think we end up studying in science as well. But this underlying model, right, is the actual forward process has this whole grammar over possible outputs, and doing inference over this is nightmarishly hard. Can anyone tell me how to specify a prior for this? Like one that makes any sense in such a way that I could compute a Bayes factor at the end of this and have it mean something. Because when I'm working with realistic models, I don't have the kind of knowledge I need to pin this kind of stuff down. And I think that's a real problem. Because if I don't have that knowledge and I'm expected to use Bayes factors, then I can't evaluate this model. Yet this model, which is like the Bayesian program induction model, is probably state of the art. But I can't evaluate it because I can't do the things that my statistics tell me that I should. So what do I do? The answer is mostly I cry. I don't actually have an answer to this, but I feel like if I'm going to get up and give this story, I should at least say something about what I try to do in real life, and I don't know if it's the right answer. But I think back to this George Box paper and the famous quote, and in its full form it says something like this: "Since all models are wrong, the scientist must be alert to what is importantly wrong. It is inappropriate to be concerned about mice when there are tigers abroad." And my complaint about things like convergence in Kullback-Leibler, divergence and things like that, or modeling low-level features of the data, is those things are mice. Most of the time I want to know something very different. I want to know about tigers. So this is the problem that we face. Every statistical tool has problems. This is how Gibbs samplers work in real life. The data you have are racist, and your models are wrong, and you have no idea how to write down priors for them. So we don't have an easy task as scientists. I like to think I've gotten smarter in how I do this, but I've mostly gotten smarter by just trying to dumb down the way that I think about these things, and mostly to be more humble. So a lot of the time what I end up doing is just trying to rely on substantive domain knowledge by the person who ran the study. What do they know about what is and isn't plausible? Should my network show racist behaviours? What kinds of patterns are plausible or interesting to find in my data? And that's going to be informed by my theory or my understanding of the scientific landscape. So I'm going to abstract some way and talk about what kinds of qualitative patterns in the data are of interest to the scientific question, and then ask questions like, to what extent is this actually an invariant prediction of my model? Like, if my model always predicts B greater than C greater than A, and I see that every single time in the data as well, that's nice. If, on the other hand, my model can produce any ordering, then that's less impressive. And in a sense, this is the same model fit versus model complexity issue, but in an abstracted representation. I'm talking only about some subset or some ways of slicing through the data that are relevant to my problem. And this is, in truth, like what we always do. Anytime you build a model, you're not building models over this P, let's not worry about the details here, but P being the space of all possible probability distributions is nightmarishly hard to work with. Nobody ever goes there. And the models we're using are this tiny little subset of things, and we're doing inference within this small world. And what we're hoping to do is project back out to learn something about this pi thing, which is the truth. And what I'm trying to do is, by specifying what patterns matter, is try to guide what inferences I make to actually say, well, look, which directions in this space are of interest, in the hope that that kind of theory-guided exploration actually helps me. So in practice, I end up asking myself all sorts of questions about what am I trying to solve, what do I want to learn by using this model. I use this picture a lot because it's got lots of pretty colors in it, but basically I've got a data set at the top and a model at the bottom. Yeah, it's hard to tell. It fits rather well. It fails. It has systematic failures. This model is absolutely wrong. Like, basically, that is a systematic failure that it can never not produce. This model is actually wrong. But I think I learned a lot about human reasoning from the experiments that I ran with it. I often don't care about this plot that just shows model performance against the data, because I'm typically interested in what are these curves looking like? What are they telling me about how people are interpreting the task? This is a kind of meaningful representation. This is just a statement of where the data falls in some abstract plot. So then I end up doing this iterative process of model building, model construction, where I will try and fit the model to the data and say, oh yeah, okay, getting a little closer, but maybe I'm overfitting. And then I go back and look again at the theoretical patterns that I'm producing, and then maybe worrying maybe this is underfitting. And so there's this process of going back and forth, of interrogating the data, modifying my model, and going back and forth between this kind of propose critique. And the curious thing is that when, this is going back to Box's paper, is that this is exactly the kind of way that Sir Ronald Fisher talked about how he went about doing his data analysis. He would very often do this, go through this process of constructing a tentative model. He would do inference, fit it to the data, and then he would criticize his own model and go round and round in circles until finally he could satisfy himself that he had something interesting. It has not escaped my attention that this would probably be called p-hacking today, which I'll let you make your own judgments. But it is p-hacking, really, in the sense that I am using the data that I have observed, which is like, see the little inkwell thing, and I'm using the inkwell to draw other ink, yeah. It was the middle of the night when I put the slides together, and I'm very tired and jet-lagged. And so I'm left wondering, where does all this fit together? I don't have answers. I'm kind of, again, I'm not really the kind of person who studies this. I'm just the scientist trying to get by. But I have this question, right? If statistical inferences don't work, or at least don't work as advertised, then they do lose their usual meaning. The Bayes factor doesn't inherently mean evidence in the way that you might think it does. The p-value doesn't inherently mean a type 1 error rate and so on, even in confirmatory analyses, because of problems like model misspecification or just having terrible data. And so I have to ask the question, why am I so worried about the same thing in an exploratory context? I'm occasionally told off because I actually do statistical inference as part of my exploratory data analysis. Because, well, you're reusing the data and that's p-hacking and that's bad, so you have to do confirmatory analyses. Otherwise, your inference loses all meaning. But it didn't have that meaning in the first place, so I'm a little bit puzzled. I do think, on the other hand, most of the stuff that we're trying to do as part of this methodological reform makes a ton of sense. Because if I've followed these processes, you need to be able to follow how I got there. So transparency, openness, audit trails, and just scrupulous honesty about the way in which I got to where I am is critical if you want to understand my data. Because you may draw different conclusions from my process, and that's okay. But I need to tell you what my process was. And I guess, you know, to the extent that I want to be slightly provocative in some of this, is I'm less sure about how much I subscribe to this idea of sort of pre-register an analysis plan and stick to it, because that does preclude the kind of cyclical model construction and interrogation process that, you know, Fisher liked and I liked and so on. And, you know, I occasionally use the language for this, thinking, well, no analysis plan survives contact with the data. You can write it down and you can pre-register that, that's fine. But when you look at your data, it will turn out that all of your guesses were rubbish. They're always rubbish. Your data are always complicated, and you have to adapt to that. Trying to stick to a plan that was so obviously wrong seems like a really bad idea to me. And so I guess my take home, because I've been listening to Nico Case lately, is more this is thinking, there are so many tools that are made for my hands, but the tide smashes all of my best laid plans to sand, and there's always someone to say that it's easy for me. And I think that's one of the reasons I get a little bit snarky at times and a little bit annoyed, because people keep telling me that they know the answers, that we know the answers, that we know how to do inference, that there is a right answer, that there is a wrong answer, and I'm not sure that that's true. Who gets to be the judge of these things? I don't know, but it's always someone telling me that it's really easy, and I'm looking at my data, and I'm looking at how many years I have spent reading statistics and thinking about these problems, and I'm not convinced it's anywhere near as easy as we sometimes say it is. And I guess part of all of that is an argument to say that we should be kinder to each other, as well as being open. And I will stop there.